Good afternoon. Just picking up where we have left off, okay, and we have been working throughout chapter 1 with functions, both individually and also in the capacity of operations between functions. And last time we looked into odd and even functions, and we have in terms of the characteristics for an odd function. Okay, again, you have f of negative x is equal to the opposite sign of f of x, signifying that additive inverse inputs will lead to additive inverse outputs. And in the case of what we have concerning even functions, okay, you're going to have additive inverse inputs to lead to the same output. And for what we have on the page of 210, and we're looking to see if the function of concern is going to be odd, even, or neither. And in the case of number 34, okay, we have the function given as p of x. And just like f of x, p of x is just another way of saying y in the xy coordinate system. Okay, so you have p of x is equal to the negative, the absolute value of x plus 12 times x to the 10th plus 5. And looking at what we have with this function, okay, and to determine whether we have it to be odd or even, you could look at it through graphing, or just looking at how p of negative x is going to follow through. And so for what we have with our given function, okay, p of x, okay, now we're looking at what will happen once we place p of negative x. Okay. Alright, so we have p of negative x. Okay, we have the negative of the absolute value of negative x. And we have plus 12 times the 10th order of negative x. And we have followed by the addition of 5. And looking at how the results will arise for both p of x and p of negative x. Okay, now this is our first encounter with absolute value functions, at least in terms of determining whether the function is odd or even. Okay, and now for the absolute value of x, okay, that is going to be at x. But now if you notice, we have the negative sign outside the absolute value terminology. And so we'll be taking the opposite sign of x, so we're going to have negative x plus 12 times x to the 10th plus 5. Now in the case of p of negative x, okay, now the absolute value of a negative is going to be a positive, so the absolute value of negative x is going to be at x, and we're still taking the opposite sign of this. Okay, so you have the negative of x is also going to be the first term in following through, and a negative term to a raised power that is even is going to come out to a positive, so we have 12 times x to the 10th. And again, we have the constant 5 to follow. And so looking at how the outputs will compare. Okay. Alright. So again, we have x and negative x as opposite inputs. But now, if you notice, we have between negative x and negative x, 12x to the 10th, 12x to the 10th, as well as 5 and 5. Okay, we're going to have the outputs to be the same throughout. And if we're starting out with additive inverse inputs and the output terms are all the same, this is going to signify that the function of concern is going to be one that is even. So for the answer to number 34, okay, is that p of x is going to be an even function. And looking at what we have in terms of how the graph of this function is going to appear, And so we have for the negative, the absolute value of x plus 12x to the 10th plus 5. Okay, we got, again, the graph of an even function is going to have symmetry with respect to the y-axis. Okay, and okay, so we got the middle point x is equal to 0, and you have the corresponding y value is going to be at 5. And then once you stray away from the y-axis or from x is equal to 0, say if you go one place to the left as one place to the right, got -1 and 1, and notice that the output values, okay, will be 16 and 16. If I go out to -2 and +2, we got the same y values, and on both sides of the y-axis you're going to have these two halves that are going to be mirroring each other. Okay, and so for the same x value you're going to have the same level at y, and so this is a case of what we have with an even function. Okay, so again, for additive inverse x values, the y values are the same, and again the graph is going to have symmetry with respect to the y-axis. Now in the case of what we have for number 35, and we have for this one, okay, so we have k of x is equal to 13x cubed plus 12x Alright, so you don't have any absolute value terminology in this one. Okay, and it looks like there's going to be no adjustment made for k of x in terms of any further clarification. Okay, so you got 13x cubed plus 12x. Now looking at how k of negative x will play out. Okay, so putting negative x in place of x. Okay, so we're looking at 13 times the cube of negative x, and we have plus 12 times negative x. And okay, now odd powers of negatives will still result as negatives. So we'll have 13 times negative x cubed. And so this will become negative 13x cubed. And 12 times negative x, so this will be a minus 12x. And looking at how the outputs relate, and we have originating, okay, from x and negative x. Again, we have opposite sign inputs, and if you notice, okay, we have for k of x we have positive 13x cubed and positive 12, whereas whenever the input is at negative x we have negative 13x cubed and negative 12x. And guess what? Throughout the outputs are going to be opposite each other. And so in this case we're going to have k of x to turn out to be an odd function. And again, an odd function is going to be a function where for additive inverse inputs the output terms will unanimously be of opposite sign value. And so just taking what we have here for 13x cubed plus 12x, okay, and in terms of graphing, this is going to fit rather tightly, and apparently running or seem to run tangent in fashion to the y-axis. But okay, we have from x equals 0, okay, we have the origin, and for additive inverse inputs, -1 leads to -25, +1 leads to 25. And say for x at negative and positive 2, we have the respective outputs at negative and positive 128. And this is a case of where instead of the same y values, we have y values that will be additive inverses. And you're going to have symmetry, not with respect to the y-axis, but with respect to the origin. And here, just for the positive values in x, the graph edges ever so slightly to the right as it goes up. But at the same extent, to the same extent you have for the negative values of x. You have the graph to slowly be progressing to the left as it moves downward. Okay. And so you have those portions mirror each other with respect to the origin. Now, for what we have in the case of our next function, okay, which we're going to have in the form of n of x, we have for number 37, okay, this time we have n of x, and that is equal to the square root of 16 minus the square of x minus 3. And looking at what we have concerning n of x as well as n of negative x. Alright, so in the case of n of x, okay, we have the square root of 16 minus the square of x minus 3. And let's say if I take care of the parentheses, now the square of x minus 3. Remember, like x minus 3 times itself. Okay, so this will be x squared minus 6x plus 9. And if I combine the constants, okay, now it will have negative over x squared minus 6x plus 9. So 9 is going to be subtracted from 16. So we'll have 7. Then we have minus x squared. And a negative over minus 6. Okay, that's going to be a plus. Made that negative over minus 6x. That will translate to the addition of 6x. Now for n of negative x, okay, so you have 16 minus the square of negative x minus 3 within the radical. Okay, and just going to move over and just taking the square of negative x minus 3. So you have negative x minus 3 times itself, and taking the FOIL, so you got negative x times negative x is going to be x squared. And we have negative x times negative 3, so there'll be a plus 3x. Inside you also have negative 3 times negative x, so there'll be another plus 3x. And negative 3 times itself is going to be a plus 9. And so for what we will have here, it's going to be the square root of 16 minus, okay, the attained trinomial, x squared plus 6x plus 9. And combining, okay, so we got 16 minus 9. So we have 7 once again, and we have minus x squared. And we're going to have 6x is going to be subtracted. Okay, so in terms of how the outputs are going to relate, okay, so we have x and negative x. Okay, those are going to be opposite each other. And okay, now for the radical terms, now you got positive radical terms. So that particular part, okay, those are going to be the same. And inside the radicals, okay, we got 7 and 7, negative x squared and negative x squared. However, we have with 6x inside n of x and negative 6x inside n of negative x. Okay, those turn out to be opposite. And since we don't have the same throughout, thanks to the offset created by the 6x from the first and the negative 6x from n of negative x, that means that this particular function is not going to be odd or even. So you have this mode of inconsistency. And so it's going to follow that n of x is neither odd nor even. And just kind of looking at this radical function. Then we have for its graph. Okay, notice you have what appears to be a semicircle, and okay, so we have for the square root of 16 minus the square of x minus 3. Okay, so you got your point, so you got x at 0, and once you get away from 0, whether it's the origin or away from x is equal to 0, where we had the y-axis, notice you don't have symmetry with respect to the origin, and you don't have symmetry with respect to the y-axis. And guess what? You don't have same y values or opposite sign y values for each of the inputs. You got like -1, 0, and if you had an odd or even function, you would anticipate 1, 0, but you have anything but that, and you might have like -2, undefined 2, you got 3.87, so this is not going to fit the bill in terms of being an odd or even function. Okay, so again, 39 is a case of where we have neither case to apply. Now, for what we have in the case of, say, for number 41 and this one, okay, perhaps the most basic of the functions from this group, and this we have with h of x is equal to 5x. Right, okay, just a single term that defines h of x. So you have h of x equal to 5x, and with the input at negative x, our output is going to be 5 times negative x. And 5 times negative x, okay, that is going to be negative 5x. So just looking at directly comparing the inputs and the outputs. Okay, so you have with x and negative x, okay, those are going to be opposite, and the outputs, okay, those are going to be opposite as well. And so we have in this case, all right, we have y is equal to 5x, or in this case h of x is equal to 5x. Okay, that is going to turn out to be not an even function but an odd function. And if I had the same output, it would be even, but since I have opposite sign outputs, okay, we have an odd function. And just a quick visual. And again, an odd function will have symmetry with respect to the origin. Okay, so you have opposite sign inputs, you got like 1 and -1, and the outputs are opposite sign as well. You got 5 and -5, and +2 yields +10, and -10 yields -2 yields -10. And again, you have both portions, okay, mirroring each other about the origin. All right. And again, so 41 is the case of an odd function. And now there will be some other functional relations and categories as we proceed throughout the course. Now, for what we have also in the group, and going back to what are regarded as piecewise defined functions, and we have for the case of number 47, okay, and we have here, okay, we got f of x, and we have is equal to, okay, and for values of x less than -1, okay, we have f of x is equal to -3x plus 7. And then we have next, okay, we have that f of x is equal to x squared plus 3. And we have for values of x, okay, for a problem we have -1 is less than or equal to x is less than 4. And then we have f of x is equal to the constant value 5. And this will be for values of x greater than or equal to 4. And just looking at the various outputs, okay, and so 47, we're looking at attaining the y value whenever x is at 3, and also whenever x is at -2. And also in the mix, okay, we're looking at f of -1. Also we have f of 4. As well as f of 5. Okay, and in terms of which of the inequality statements the respective inputs will belong. Okay, so for 3, input value of 3 is not less than -1, so it's not going to be -3x plus 7 that is applied. 3, well, it is greater than -1, so to state that -1 is less than or equal to 3 is less than 4, okay, that is going to apply. And so, since this is the inequality, we're going to use the x squared plus 3 mode of operation. So we have x squared plus 3. So this will be 3 squared plus 3. 3 squared is 9. And 9 plus 3 comes out to 12. Okay. Now for -2, okay, -2 is less than -1. And in terms of what to do with -2, we apply the -3x plus 7 treatment. So we have -3 times -2, followed by the addition of 7. Negative times negative is a positive. Here we have a positive 6. And we have adding 7. So the output comes out to 13. Now for f of -1, okay, now -1 appears in the first and second inequality statements. And now -1 cannot be less than itself, so the first part is discontinued or scratched out. Now -1 again cannot be less than itself, but it is equal to itself. And in turn, -1 is less than 4. And so just like 3, -1 belongs to the second inequality description, and so we're going to apply the x squared plus 3 route, and so we'll have -1 squared followed by the addition of 3, and the square of -1 is +1, and we have plus 3, and 1 plus 3 is equal to 4. Now for f of 4, just like the number 1, okay, 4 appears twice, and the inequality to which it's going to belong, okay, now 4 cannot be less than itself, nor can it be greater than itself, but it is equal to itself, and the equal sign appears in the last of the inequalities. Okay, so 4 is greater than or equal to itself, and any value of x that is 4 or greater, the function value is going to come out to the constant value of 5. And for f of 5, you had this bit of history to repeat. For 5 is greater than 4, and that will belong to the last inequality statement, and the matching function for f of x, that is going to be at 5. So just like f of 4, f of 5 is equal to 5. Okay. So you have yet another piecewise defined function. And now for what we have in the case of number 48, okay, now we have a function g of x. And this is broken up into separate sections, and the first we had to look at carefully if it is applied. And here we have -2 times the absolute value of x followed by the subtraction of 3. Okay, for those values of x less than or equal to -2. Then we have g of x is equal to 5x plus 6. And that'll be used for those values of x, okay, whereupon negative 2 is less than x, which in turn is going to be less than 3. And then for the remaining values of x, okay, we have g of x is equal to the constant value 4, and this will be whenever x is 3 or higher. Okay, so x is greater than or equal to 3. And we have for the various inputs, now we've got g of negative 3, and we have g of 3. Then we've got g of negative 2 as well as g of 0, and g of 4. Okay, so looking at the inputs, and we have for g of negative 3, negative 3 is for x, and negative 3 is less than negative 2. So the first inequality statement with x at negative 3, that is going to ring true. And so for g of negative 3, we've got negative 2. Absolute value of x is going to be the absolute value of negative 3. We have followed by the subtraction of 3. And for the absolute value of negative 3, again, that is going to be a positive 3. And for the follow through, okay, so you got negative 2 times 3. Okay, we have followed by the subtraction of 3. Negative 2 times 3 is negative 6. And negative 6 minus 3, okay, that is going to become negative 9. Now for what we have in the case of 3, okay, that appears twice, and looking at testing out 3, negative 2 is less than 3, however 3 cannot be less than itself, and where we have 3 in the last inequality statement, 3 is not greater than itself, but it is equal to itself. So thanks to the equal sign, the last inequality rings true. And so for g of 3, anything that has a value of 3 or higher for the inputs, the output is just going to be the constant value 4. And like 3, negative 2 appears twice among the inequality statements, limits. And for what we have here, for negative 2 is not less than negative 2, but it is equal to itself, and the first statement is going to apply. So we do have that negative 2 is less than or equal to itself. And for g of negative 2, so we have the reapplication of the absolute value term. So we now have negative 2 times the absolute value of negative 2 minus 3. And the absolute value of negative 2 is positive 2. So we've got negative 2 times 2 minus 3. Negative 2 times 2 is negative 4 minus 3. And we have for that final answer, okay, this will end up as negative 7. Now for 0, okay, and 0 lies between negative 2 and 3. And in terms of what to do with 0, okay, we have the entry of the 5x plus 6 portion. And with x at 0, so we got 5 times 0, followed by the addition of 6. 5 times 0 is 0 plus 6. And so g of 0 is equal to 6. Now for g of 4, okay, and 4 is greater than 3, and so again, 4 is an input that is at least 3 or greater. And so for the output, okay, you have the history of case number 2 revisited, and g of 4 is equal to 4. Okay, and now looking at what we have and just sort of expanding the model, and we have for number 50, we have a remaining piecewise function, and this is given whereupon we have y is equal to t of x and we are looking at 4 tiers here. Okay, you have like for first case, you have for the starting values. Okay, you have t of x is equal to x, and now for the inputs, okay, the full expanse is not going to arrive at anything that is remotely close to the real number system. But we're going to have t of x is equal to x for 0 is less than x is less than or equal to 1. And we have in the next round we have that t of x is equal to 2x, and this is going to be for values of x, whereupon we have that 1 is less than x is less than or equal to 2, and we have that t of x is equal to 3x, and this will be for values of x, whereupon 2 is less than x is less than or equal to 3. And we have also t of x is equal to 4x, and this will be for those values of x whereupon we have that 3 is less than x is less than or equal to 4. So we have for the full expanse, instead of just running the whole gamut of the real number system, we're just looking at like everything between let's say positive numbers running past 0 and maxing out at 4 for the inputs. Anything out of those boundaries is not going to be applicable for t of x inputs. And we have for the values of x whose corresponding y values we are to configure. Okay, so we have the first item, okay, we have t of 1.99. Also you have t of 0.4. Also we have t of 3. As well as t of 1. I also have t of 3.001. Okay, so just looking at the inputs. Okay, so 1.99, it does belong in one of these inequalities, and so it's going to fall between 1 and 2. So it is true to say that 1 is less than 1.99, which in turn is less than or equal to 2. So for t of 1.99, it belongs in this inequality, so we're going to apply the 2 times the input treatment. And here we're going to have 2 times 1.99 and 2 times 1.99. Okay, that first part is going to yield 3.98. Okay. Now for 0.4 belongs as an input, and this will fall between 0 and 1. So we have that 0 is less than 0.4 is less than or equal to 1. And in terms of what to do with values of x that lie in this particular inequality, well, the input x is just going to become the output, okay, which you have at t of x equal to x, but t of 0.4 is going to lead to 0.4. Now, in the case of what we have with t of 3, okay, so 3 appears twice, and we have to spring forth, okay, as a limit or something tangent to it in the last and next to last inequalities. And where 3 belongs, now we got 2 is less than 3, that is true. And while 3 is not less than itself, it is equal to itself. And then with the other inequality, well, 3 cannot be less than itself, and we don't have the equal sign. And so the last inequality is irrelevant. So only the third one applies. So we got 2 is less than x is less than or equal to 3, whereupon x we have to be at 3. So for t of 3, we're giving it the 3 times the input application, and 3 times 3 becomes 9. Okay. And in the case of the number 1, okay, 1 cannot be less than itself, but it can be equal to itself. So the first inequality is going to apply. And so for what we have in the case of t of 1, t of x is equal to x, what Well, with x at 1, t1 is equal to 1. And for 3.001, okay, this is our only specific input that happens to be greater than 3. And 3.001 is going to fall between 3 and 4. So we got 3 is less than 3.001. And that in turn is less than or equal to 4. And for the values that lie between 3 and 4 in this fashion are going to be quadrupled. Okay, so in this case we have the 4x treatment, where we have 4 times 3.001. And so we have for this output, okay, this is going to become 12.004. And that'll be the final answer for what we have among these compositions. All right, and again, regarding characteristics of functions, okay, we've had like symmetry, like concerning odd as well as even functions, and so we're going to be looking at in behavior of the graphs of functions, okay, and the functions, they may be odd or even functions, or they might not fall into either category, and just kind of using as a set of building blocks. And see, like just looking at end-to-end behavior and activity in between. Okay, now this next part is going to have a little bit of a long title to it, but we're looking at like particular sections, okay, where the graph might, you know, rise and fall in between certain points and sections. And now we're looking at what will be regarded as relative minimum and maximum. For increasing and decreasing functions. It's a bit of a long title, but the stuff like relative minimum, maximum, and where functions increase and decrease, the concepts do go hand in hand. And to give you kind of an idea about all these items, okay, we'll start out with the graph. Not drawn according to scale, but just to kind of show what we mean by minimum, maximum, and also where the function increases as well as decreases. Okay. Again, so you have the y-axis and the x-axis. And so we have among the points, okay, so we have, again, not drawn according to scale. Let's say we have -1 and 0.5. We have 0.5, -3, and these are ordered pairs. Also, we'll say that we have another ordered pair, okay, where we have 5, 2. And yet another ordered pair where we have 5.5 and 1. And say we'll have a function f of x and it's going to run through these 4 points. Okay, notice you have a little bit of a zigzag. You have up and down, and back up. And let's say that regarding the graph of this function, okay, there'll be some items to determine. Okay, first of all, okay, regarding relative minima and maxima. Okay, first of all, if I were to determine the relative minima of f of x, okay, now for the minima, you can just call those the locations where you have the dips to occur. In other words, the sections where the graph is momentarily bottoming out. Okay. And so for what we are looking at, where you have just like your you have an increase and you have a decrease, and notice you have a bottoming out at 1/2 -3, and then you have it starting to go up, and then it kind of peaks out at 5 and 2, and then it starts to fall and then rise up again, and that bottoming out occurs at 1. So for the relative minima of f of x, okay, this is going to be where we have y is equal to -3, and also where we have y is equal to 1. And if you were to determine where the relative minima occur, okay, those are going to be the x values that correspond. Okay, so at the first relative minimum, okay, we have when y was at -3, your x value is at 1/2. And also whenever we have y at 1, okay, we had x was at 5.5. Okay, so this is what we have regarding the relative minimum. Okay, now in terms of where we have the maxima, the relative maxima to occur, okay, yeah, so the relative maximum, okay, instead of like the dips, okay, you'll be looking at the peaks, the relative peak points. And again, we're looking at y values, and we'll say that we have for those y values. Okay, so you have an increase, and you have sort of reaching a peak before starting to settle down. So one y value, you have it 1/2. You have bottoming out, and then you have to rise up, and then you have to dip once again. So the relative peak point here we have to occur at y is equal to 2. And where these relative maxima occur, And so we're going to have for those corresponding x values. Okay, so y at 1/2, this will occur at x is equal to -1. And where we have y equals 2 to be the other occurring relative maximum. Okay, we have the x value of 5. Okay, so you got your relative minima and maxima. And when you're talking about relative minima or relative maxima, you're looking at the y coordinate aspect of those terminologies, and where they occur, you're looking at the x coordinates. And now, regarding this particular function, okay, and again, had the other part here, relative minima and maxima for increasing and decreasing functions. And we have for the remaining description, at least at this stage, so you have determining the intervals of increase and decrease. For f of x, okay. And so just for the intervals of increase and decrease, you're looking at reading the graph in order from left to right. Okay, so you have interval or intervals of increase as well as decrease. Okay, and so just looking at what we have in the pattern. So you're reading the graph in order from left to right. Okay, so the first bit of motion, okay, you have an increase. Okay, so the graph is moving up as you proceed from left to right. You have an increase, but past this relative maximum, okay, you have a downward motion, so you have the graph to be decreasing. And then once you get past the relative minimum, okay, you have the graph to increase. Then past 5.2, you have it to decrease. And then once you get past the second and last relative minimum, okay, the rest of the graph of f of x is going to be moving upward. Okay, so you have an increase. And for those intervals, now you're going to use parentheses, but the parentheses will not be used in the case of like identifying points, like these ordered pairs here. We're looking at just the x values. Okay, so for what we have for the increase, okay, so you're starting from the leftmost region, and the arrowhead that we have pointing downward, this is in reference to the farthest reaches of x in the negative zone. So we have proceeding from negative infinity, and we have approaching and not including, okay, that x value which we have at -1. So between negative infinity and -1. And the next increase you have going past x at 1/2. And we have approaching 5, as in x equals 5 on the point 5.2. And then for the final increase, okay, you have the last section of f of x, and be for those values of x that will be greater than 5.5. And we have going all the way out to infinity. Right. Now, for what we have regarding the intervals of decrease, okay, so the first bit of activity you have between -1 and +1/2. And with the second and last portion where we have decrease, so we're looking at going past 5 and approaching 5.5. And again, for intervals of increase and decrease, okay, we're looking at exclusively the use of parentheses. Okay, so you got 5 intervals, sections. Okay, so you have 3 on the side of increase and 2 on the side of decrease. Okay, now let's say that if we have, say we have the function and just in comparison to what we just had up, okay, I'm just going to change the motion dynamics a little. Okay, now we'll say we have among our points, okay, we'll say we have -10, -6, also say we have -3, -2. Let's have 1, -5. I also have 3, 2. Again, these are just XY coordinates. Now say we have 4, -1. And then we'll say we finally have 5, 6. Okay, and so just to kind of consolidate, let's see what we get for all the characteristics that we have for the graph of f of x. And what I mean by 1 through 5 is that first of all determine the relative minima, where the relative minima occur, and then determine the relative maxima and where the relative maxima occur, and then finally the intervals of increase and decrease for this particular function. So just determine what those characteristics are, and we'll discuss in the next few moments. Okay, for what we have regarding this function f of x, okay, so we have in the mix, okay, so we got 6 specified points, and those specified points each one of them is either going to be a relative minimum or a relative maximum. Okay, now for the relative minimum, okay, we're now looking at referencing the y values that correspond. Okay, and so we have, just reading from left to right, so you have for your, again, your bottoming out points, okay, -10, -6 is such a point, so you got y at -6, and the next bottoming out point we have at 1, -5. We have one more bottoming out point at -1. So for the relative minimum, okay, we have y equal to -6, also y at -5, and also at y equal to -1. And where the relative minima will occur, okay, those are going to be the corresponding x values. Okay, so we'll have -10 whenever y is at -6, and when y is at -5, okay, we have the x is equal to 1, and when we have y at -1, the corresponding x value is at 4. And for what we have concerning the relative maximum, okay, and those are going to be, once again, the relative peak points. So for the relative maximum, okay, so those are going to be the peaks. Let's see. Yeah, let's have y at -2. We have next relative peak at y is equal to 2. And then we have the third and the last, we have at y is equal to 6. And where those peak points will occur, okay, we have for the corresponding x values. Okay, so whenever y is at -2, corresponding x value is going to be at -3. And whenever we have y equal to 2, the corresponding x value was at 3. And for y is equal to 6, we have the corresponding x value at 5. So this will be where all these relative maxima will occur. Right. Now, in terms of the intervals of increase and decrease, okay, so just reading the graph in order from left to right. Okay, so first bit from left to right, not right to left, but left to right, you have a downward motion, so you have a decrease. Then past 10, -6, you have an increase. You have followed by a decrease, and you have alternating, kind of a sawtooth pattern. We have alternating decreases and increases. And so it looks like we've got 3 intervals of increase and 4 intervals of decrease. And so just looking at what we have here. Okay, so for the intervals of increase, okay, so you're looking at between -10 and -3. So you're looking at just the x values and the interval notation. So between -10 and -3. We have the increase between 1 and 3. And also have between x equals 4 and x equals 5. But again, we're not including those endpoints. Okay, so all the x values are left in parentheses. All right, so between -10 and -3, between 1 and 3, and between 4 and 5. Now for the decrease, okay, this is where we start off from the left. Okay, so you have between -infinity and -10. Also have between -3 and 1. And also have between 3 and 4. Now for the remaining activity, we also have a decrease, and this is for all values of x greater than 5. So here going past 5 and all the way out to infinity. Okay. All right. And so that'll be the summary of what we have for the intervals of increase as well as decrease. All right. Now, for what we have regarding the zigzagging between the relative minimum and maximum. Okay, there is an element of this where you can sort of determine the power or the degree of the polynomial function, and all those collective minimum and maximum, those will be what are referred to as turning points. And for what we have in the case of turning points, okay, we have just an introduction. Okay, so we have for a polynomial, of the form, a polynomial function of the form whereupon we have f of x is equal to a of n times x to the n is a of n minus 1 times x to the n minus 1. Okay, so you have for a polynomial function of the form, okay, where n is the degree of the function. Okay, so n is going to be the degree of the function. Okay, now one might ask, okay, where are the turning points? Where are they going to come into the scene? Well, they will now. Okay, the number of turning points. Will be at most n minus 1. So just referencing. Okay, so we got n is the degree of f of x, and the number of turning points will be at most n minus 1. Okay, so in essence, what this is saying is that the degree of f of x okay, will be an odd number more, or I should say an odd amount more than the number of turning points. By at least 1. Let's give you a visual. on this one. Okay, see if we have like for a function, yes.
Before you move on, where it says AM, what is
A
that?
of n
What
x.
is that?
Those are just going to be numerical coefficients.
Okay.
Yeah. In other words, if I have like if the leading term had to be like 4x cubed, like 4 would be the a of n, and x to the n would be x to the third. It's just kind of like general notation for like f of x is equal to, let's say, like 5x to the fifth plus 7x to the fourth plus 3x cubed, and that a naught is just going to be like just a standalone number without the x alongside it.
Okay.
Yeah. Yeah, we're gonna get further into this once we get into stuff like in behavior. But just let's say if you have a function, okay, we're not going to identify it, okay, but we will let me put up some random points here, and don't even have to label. Okay, and so turning points, this would be just like the total combined number of relative minimum and maximum. Okay, so in other words, you're counting up the total number of peaks and dips, so to speak. And if you notice, okay, we have here, okay, we're going to have 4 turning points. So you got 4 turning points here, and what the degree of f of x could be, not that it will be, but could be. Now remember, okay, the number of turning points will always be less than the degree of the function. Okay, so, and we have for the degree, okay, it's not going to be 3 or 2 or 1, okay, but the number of turning points will be at most n minus 1, and the degree is going to be by an odd amount more than the number of turning points, where the difference is going to be at least 1. Okay, so the minimum possible degree of f of x is going to be 5, and if it is not 5, okay, the next number that will be an odd difference as opposed to one difference. So 3, okay, you have where the degree could be 7, or it could be 9, or some other odd higher number, or higher odd number. So it's going to be an odd difference between the power of the function and the number of turning points. Okay, so you can have 5, 7, 9 among the values to which we can have applied as the degree of the function. And I'll just throw in this one more case here. Okay, so looking at the combined relative and maximum. Okay, you have what's going to be 7 turning points. And for the possible degree of this f of x, okay, it's got 7 turning points. Okay, and again, the degrees mean more than the number of turning points, and the difference is going to be an odd value. Okay, so the minimum possible degree of f of x, okay, that is going to be 8. And if it's not 8, it could be 10. And if it's not 10, it could be 12. And if it were anything else, it'd be like just some higher even number. And whether the degree is going to be in something that's in reference to an odd number or an even number, we'll look further into that, okay, and what will be regarded as the end behavior of the graph of a function.